Hello, everyone. I'm a PhD student at Northwestern working with Fred Yasio, and today I'm going to be talking about my recent work on boosting the spins of stellar mass black holes through tidal disruption events in dense stellar environments, with some important implications for the gravitational wave sources from merging black hole binaries. So since the first detection, the LIGO Virgo Observatory has observed dozens of black holes through detection of gravitational waves. And in this plot, you see the mass range of black holes in blue, ranging from 5 up to around 200 solar mass. Despite the growing number of these systems, we still don't know where these binary black holes come from. So the two main proposed scenarios are dynamical assembly of binary black holes in dense environments, which I'm going to be focusing on today. The other side is isolated binary evolution, where you can have stars undergoing common envelopes, still will mass transfer, which I'm not going to be talking on this today. So globular clusters may account for a significant number of LIGO Virgo black hole mergers, and this is basically thanks to the large number of stars in a small region, and then in this case you can have these black holes interacting with each other frequently. So a typical cluster is born with millions of stars of different masses, and these massive, some of the massive stars become black hole, and then they sink towards the cluster center through dynamical friction, and then these interactions between black holes will cause some binary black holes to form, and then through the repeated encounters, these binary black hole systems will harden over time, and they will leave the interaction with some recoil velocity, which depends on the semi-major axis of the binary. So as the binary hardens, the recoil velocity increases, and until the binary is either ejected or merges inside the cluster. So several studies shown that globular clusters may account for significant fraction of the black hole mergers, and these are at a comparable rate to the LIGO Virgo merger rate. So binary black hole parameters such as their masses, their spins, and eccentricities at merger, these are determined by their properties when these black holes form, and then also their properties might be affected by the binary evolution. So the distribution of these parameters provide us a promising way to distinguish some of the binary black hole formation mechanisms. It can be either isolated or dynamically assembly. So in this talk, I'm going to be focusing on spin distributions of these systems to determine whether these systems are formed in the field or in the globular clusters. So far, gravitational wave experiments measure best is the effective spin parameter. It's kind of a mass-weighted projection of the black hole spins onto the orbital angular momentum of the binary, and it's given by this expression. So the gravitational wave observations shown that there is a slight preference to the positive chi-effective value, which means that spins and the orbital angular momentum of the binary black hole system is aligned. But one needs to be careful interpreting these results, because this can lead to conflicting conclusions regarding the distribution of the spins. For example, I am showing you the spin magnitudes and the angle between spins and orbit and the chi-effective. So for 3 different populations here, we have the same chi-effective distribution shifted slight to positive value. We can have different spin distributions with different inclinations. So you can obtain this chi-effective distributions for high spinning, but the anti-correlated systems, or with low spins but aligned systems, so that it can kind of accumulate the effect. So in the isolated evolution, you have binary black holes. These are formed from the stars born in the same binary. So you would expect their orbits and the spins to be correlated. So you would expect their chi-effective value greater than 0. However, in the case of dynamical formation, these black holes binary black holes are formed after their stars become a black hole. So you wouldn't expect any correlation between their orbits and spin. So you would expect this angle to be isotropic, and it peaks around 0. But none of these mechanisms could explain the slight positive chi-effective value. So this would pose challenge to dynamical formation in clusters. So instead, although it is less measurable, I think what is really important is their spin magnitudes other than their chi-effective value. So theoretical studies suggest that most single black holes are born very slowly rotating, like around 0.01 dimensional spin magnitude. However, we see that recent observations indicate almost more than half of the binary black holes contain non-negligible spin magnitude. So we can spin up initially non-rotating black holes in dynamical environments. One of the ways is these black holes can undergo repeated mergers, and therefore producing second generation black holes with higher masses, and then their spin peaks around 0.7. So the other scenario is if you have a very dense star cluster, and if the binary fraction is very high, you can have this time stars colliding with each other and then forming a very mass star, and at the end becoming a black hole. So these stars, after merging, they would probably lose their envelope. So it might be easier for them to retain their spin through not efficient angular momentum transport, but it's not very clear what kind of spin values you would get. The last one I'm gonna talk about today is black hole star collisions. So black holes are indeed likely to interact with stars, and then this could eventually the tidal disruption event. So I investigate how this kind of collisions affect the properties of binary black hole systems, especially the ones that are LIGO-Virgo sources. So here I'm gonna show you a hydro simulation of a binary black hole. Each one has 10 solar mass with a 1 solar mass star, and this star is created with the stellar evolution called MESA. And the initially binary black hole is very compact, and when the binary black hole disrupts the star, it can accrete a significant fraction of the debris, and this could effectively change the spins of each binary components. And this is kind of like similar to common envelope scenario in the field. So the accretion of the gas can actually act to align the spins of individual black holes, but this is yet to be explored. So here, I'm gonna quickly show you how we can modify the spin magnitudes and the directions of black holes through tidal disruption events. So once the star is disrupted, it will quickly form the accretion disk around the black hole in the scales of hours, and then after the stellar material is accreted, the black hole will spin up. So assuming that in the first scenario, only half of the star is bound to the black hole and the remaining is ejected, we calculate what is the mass accretion rate, and Kyle showed that these kind of interactions lead to thick disks, so it's very super Eddington. But he also mentioned that not, like almost 10% of the stellar material is likely to be accreted, but this kind of collisions might lead to different, like a kind of collapser scenario, like you can have more efficient, you can have accretion more efficiently. So the accretion timescale is order of months, but these binary black holes will later interact with other stars or with other black holes on timescale millions years, and then they will harden and then they will merge at the end. So the change in the magnitude will be the most dramatic effect and the permanent imprint, but the spin orientations can be aligned or anti-aligned, but it's unclear right now, so it's a future work. So here I'm gonna show you some of our results from embodied simulations of globular clusters with around million stars initially, and these are very compact. Their initial real radius is 0.5, and we assume 5% binary fraction, and these systems are evolved up to 14 gigayears. So I have two different models on the left and right. The left one is the high mass binary fraction. Those are stars more massive than 15 solar mass. We have just 5%. On the right, we have 100%. So we see immediately that in the blue lines, as we put the massive stars in binaries, we increase the TDE rate by a factor of 2. Also, you can see binary black hole mergers, they don't change much, but more than 50% of these merging binaries underwent a collision before they merge. So this could definitely change their spins before they merge. Another thing we observe is black holes can interact with very massive stars at early times. So on the left, when the time is less than 1 gigayear, I am showing the mass ratio distribution of the colliding objects. So you can see in the clusters with 100% high mass binary fractions, you can have collisions with black holes and very massive stars, like their mass ratios can be even 1 or larger than 1. But later times, you wouldn't expect these kind of collisions. It's usually low mass stars colliding with black holes, so that wouldn't affect their spin magnitudes or any other parameters much. So this is on the left is a stellar mass distribution over time for different stellar types, main sequence or giant stars. So initially you see on the top left we have lots of collisions happening with very massive stars, and the 60% of these are giants with median mass 10 solar mass, and the 40% of these are main sequence, and median mass is 1. But I want to emphasize that this is a core collapse cluster, so it's very dense. So in regular clusters, maybe you would expect main sequence rate to be higher, but specifically I'm interested in this cluster. So for the rates of collisions between single or binary mediated interactions, you see on the right, I'm showing you the mass of the star, and if the star is single or binary when it collided with a black hole. So giant stars the single giants have a larger cross-section because they're like bigger, and then they don't need to be in a binary to increase their cross-section. So you can see the orange, sorry, I didn't update this. This has to be reversed. I'm sorry about this. So I will say single giants are undergoing TDEs more, and you can expect more collisions for main sequence stars in binaries, which would increase the cross sections for low mass stars. So I also calculate the spin magnitudes of these black holes as a function of the accreted mass. So for this, I use analytical expression Bardeen this formula. It depends on the last stable orbit radius and how much black hole mass is changed. So you can have maximally spinning black hole if the black hole accretes some fraction of the, if the black hole gets like some factor of its initial mass, like square root of 6. And these different colors represent different initial black hole masses. So the main point here is the more you accrete, you get higher spins, and it is easier to spin up smaller mass black holes compared to higher mass black holes because smaller mass black holes require less amount to accrete. So the final spin of black holes depends strongly on the mass ratio. So this accretion efficiency changes the picture a lot. So the color code is spin magnitudes, and I am showing the masses of the black holes and stars colliding. So if the accretion efficiency is 10%, you would expect these black holes to gain spins with magnitude less than 0.5. But if you have 100%, which is not very likely, their median value is 0.5. But the total accreted mass is limited by the mass bound to the black hole, which here I assume it's only the half of the stellar mass that is bound. Lastly, I will just show a comparison for the component spin distributions of binary black holes with the LIGO-Virgo observations. So you see this kind of a agreement between the results, but this picture will definitely change with the accretion efficiency, but it clearly shows black holes that are not spinning initially. Their spin values can be changed a lot by these stellar collisions, and then we can have better predictions or distributions for their spin magnitudes. So I will conclude. Maybe I will just skip this, and I will just say the next steps. So we will perform some detailed hydro calculations to specifically check how much you can change the orbital parameters of binary black holes through these collisions. Can we increase the binary black hole merger rate in globular clusters, making these black holes harder through tidal disruption events? And also we want to look at retention of higher generation black holes and some transient signatures of these events. And then the next step is to perform some GRMHD simulations to predict accurately the accretion efficiency. And actually, what is the spin change if the disk is not equatorial plane, if the accretion disk is aligned, how much indeed you can accrete. So yeah, I will stop there and happy to take any questions.
Awesome, looks like we've got a few questions. Go ahead.
Naively, I would have guessed that half of the TDEs would spin down the black hole because they don't know which direction the spin is.
So since these are initially non-rotating, they will spin up, but if they undergo multiple stellar collisions, you can spin down. And
So how many TDEs do you need to get to 1?
So you can have one TD with maximally spinning black hole if the mass ratio of the final to initial black hole is greater than square root of 6. But this is under the assumption that the disk is in the equatorial plane of the black hole. So if the disk is inclined, you would need more mass to be accreted, I guess.
Yeah. And the Bardeen model is a thin disk assumption, right?
Can you?
The Bardeen spin-up is a thin disk assumption as well.
Yes, there is also a thin disk, exactly. So that's why we want to do this GRMHD follow-up work.
Okay, thank you.
Yeah.
Yeah, I think I was going to ask something similar, but I was trying to get a sense from Kyle's talk, because he was emphasizing that the black hole mergers happen in the mass segregated heavier ones in the center, and that these collisions are happening further out. So is it the same?
Yeah.
So is the same black holes that are experiencing the TDEs that ultimately merge?
That's a great question. So yeah, it's the same black holes, and the massive stars also segregate, but I guess since their cross-section is high, they can collide with black holes before they all sink to the center. But yeah, in the low mass binary, in the clusters where we have low mass binary, high mass binary fractions, this doesn't happen much.
I guess related, I could ask another question. So a typical, I'm still trying to get a sense of the numbers. So a typical black hole that ends up merging and making a LIGO source, how many of these TDEs has it experienced? Has it just
50% of merging.
50. So half. So
Yes,
everyone
half.
has experienced half of one. It's not like they've experienced 10 or something. So
Yeah, half of these can be affected by TDEs.
okay, because then so then maybe this spin up, spin down thing is not as relevant. Okay, thank you.
Hello, thank you. Very nice talk. So I would like to ask, to say that it's possible to provide a fast-spinning black hole by accretion of like a significant amount of mass from a star. So I'm asking about, how about like the momentum of the star? So if it's a like comparable mass to the black hole, is that going to unbind the black hole binary, or at least change some eccentricity of the binary?
Yes, that's a good question. It can change definitely the orbital parameters of the binary, like semi-major axis or eccentricity. It depends. I start to explore this regime, but I don't have any definite results. But yeah, sometimes you can even separate these black holes. They are not bound anymore, or sometimes you can make them very hard, like kind of decreasing their merging time scale. So yeah, it's not clear yet.
We should expect there might be some like relations we can find from LIGO data about like the eccentricities and their correlation with these spins if they are from this channel, something like that.
Yeah, I think that is possible.
Okay, thank you.
All right, then let's thank Fulya and all of our morning speakers again.